Welcome to Ask and Learn.
Consider a slender rod AB with a weight W drawn here from the center of mass, which is attached to two blocks A and B, which can move freely in the guides as shown. A and B are also attached by a spring as shown, and we know that the spring constant of the spring is K, and that the spring is unstretched when AB is horizontal, as in when this angle theta that they've defined is equal to 0. So we'll call that theta naught for the equilibrium. Theta naught is equal to 0, which also tells us that the equilibrium length of the spring, since AB will be horizontal, means that the spring is also the length of AB, which is given to us as L. So I'm going to call that X naught is also equal to L. Now, neglecting the weight of the blocks, we want to derive an equation in terms of our givens theta, W, L, and K that will be satisfied when the rod is in equilibrium. And this is a fairly straightforward thing to do. What we want to do is identify which forces can do any virtual work on our system, express their potential energies in terms of a single variable. In this case, we'll go with this theta they've defined for us, such that we can therefore easily use the equilibrium condition that the first derivative of the potential energy with respect to that single variable, in this case theta, is equal to 0. And we can use that known equilibrium condition to then solve for the theta corresponding to that equilibrium. And first things first, it's pretty simple what forces are at work here. It's just going to be the weight of the rod AB and this spring force from this spring that's being stretched out by rod AB moving away from horizontal. And we know the expressions for both of those. And again, those are the only forces that can do any virtual work on our system, because while the guides A and B are in provide like normal force supports, they're not doing any displacement on our system, so therefore no work. And we're going to just look at the spring and the weight. And so our total potential energy is the elastic potential energy of the spring plus the potential energy due to gravity, i.e. the potential energy of the weight. And we know the expressions for both of those. The elastic is 1/2 kx squared, where k is the spring constant and x is the amount the spring has been distressed, either stretched or compressed from its equilibrium length. And then plus our just the force, our W, times the y position of the center of mass. We're going to call that y sub AB. And again, we want to get these all in terms of theta. So we can go ahead and say that our x for the spring, which is going to be basically segment BC plus segment AC, the two sides of our triangle, is going to be equal to L times L being the hypotenuse of our triangle here, the length of AB. So L times cosine theta, i.e. our adjacent, plus L times sine theta, i.e. our opposite, minus 1, because we're minusing L, the equilibrium length. And our YAB is similarly just going to be negative L over 2 sine theta. Why is it negative? Because we're going to define the below our equilibrium origin point of when the spring's equilibrium point of theta equal naught as our origin. It doesn't really matter as long as the two potential energies are opposing each other, because they're clearly not additive in this scenario. The spring is not helping the weight further stretch it out, it's opposing it. So then we can sub these in and get our general expression for the potential energy. So V equals 1/2 K times the quantity L times cosine theta plus sine theta minus 1, and quantity and bigger quantity squared minus, again, just W times L over 2 sine theta. And again, this is just minus because we need them to be opposing, and that's how we've defined our coordinate system, is this is the negative one. So we can go ahead and take our first derivative with respect to theta to go ahead and get after using the equilibrium condition to find the equilibrium positions. And this is just, I'm going to pull out a KL squared. The half cancels from the power rule coming down. These are all pretty easy derivatives because they're just basic trig and chain rule. So we got quantity cosine theta plus sine theta minus 1 times its chain, the quantity cosine theta minus sine theta, and that quantities. And then again, this is just minus WL over 2 cosine theta, just super easy trig derivatives. And we can clean this up a bit to get it to be the first derivative with respect to theta is equal to KL squared times cosine 2 theta minus cosine theta plus sine theta, and then just again minus WL over 2 cosine theta. And now we want to go ahead and use that equilibrium condition and set this equal to 0 and rearrange a little bit to get our like terms on different sides of the equation, but we get a final equation in terms of K, L, W, and theta of KL times the quantity sine theta plus cosine 2 theta equals the constants in front of KL plus W over 2 times cosine theta. And that is our general equation for our system that is satisfied when it is in equilibrium.